Keep in mind, Brayton cycle is also called as Joule cycle. Right on. It is also called Joule cycle. So what are the contents in today's topics is, first we'll understand what is open cycle gas power plant. And all gas power plants that is work on the principle of Brayton cycle. So open cycle gas power plant. There is one more closed cycle gas power plant. We'll also understand the difference between these two in the next classes. So once you understand the open cycle gas power plant, then you will draw PV and TS diagram for Brayton cycle for open cycle. Understood? So PV and TS diagrams are the most important for solving numericals. For solving numerical, so these TS and PV diagrams are important. Next, in these processes, there are 4 processes involved. In the Brayton cycle, there are 4 processes. We'll explain, don't worry about it. Out of 4 processes, someone is heat addition will be there always and rejection. You will be writing mathematical equation for these 2. Mathematical equations. For heat addition, what is the equation of QS, QR, and as well as work done expression. So we'll be writing the expressions for all the 4 processes. Next, I'm extremely sorry. I got so cold. Please manage. And also work done expressions. Then we will write an expression for efficiency of the Brayton cycle. That is eta efficiency using the point number 3 and point number 4 processes. Using heat addition, heat rejection, and work done expressions, we will write efficiency of the Brayton cycle. Next, we will understand the closed cycle gas power plant. First, what we do is, today we discuss up to 1 to 5. Point number 1 to point number 5. So first, keep in mind, Brayton cycle is also called as Joule cycle. That is important. Some textbooks, they also write Joule cycles. In some of the exams, they also explain Joule cycles. It is same as Brayton cycle. And all gas power plants works on the principle of Brayton cycle. Okay. Next, we'll move to open cycle gas power plant. So I have taken these pictures. This is the diagram. And dear student, just to have a look on the first diagram. So let me call it as first A. This one I will call it as B. This one I will call it as C. So picture B and C are PV and TS diagram of this Brayton cycle. Okay. Now look at the picture A, whether it is open or closed. Understood? See, it is open cycle because the exhaust point is not connected to the inlet point. So if you connect the point number 4 with point number 1, so then it will become a closed cycle. So as of now, it is an open. And keep in mind, when you connect point 4 with point number 1 with some pipeline or whatever maybe, then one more device will come here. That device we will call it as heat exchanger. What is the 4th component? Heat exchanger. But here in the open cycle, the heat exchanger is not there because it is, as the name indicates, open. Okay. So now I will remove. I will erase this. First we will understand open cycle. Then we will understand the closed cycle. Okay. So first point, what is Brayton cycle is? So Brayton cycle consists of three major components. First one is compressor, second one is combustion chamber, third one is turbine. So combustion chamber is represented with CC, and third one is turbine. And if it is closed cycle, the one more component will be added, just is heat exchanger. So if it is a closed cycle gas power plant, then we will not call it as combustion chamber, the second component. We will call it as heat exchanger 1. This will be heat exchanger 1, and one more will be heat exchanger 2. That is for closed cycle gas power plant. But here we are discussing open cycle gas power plant. So we will call it as it is combustion chamber. And there is no heat exchanger. That's the first point. Second point, a representation of these components. And dear students, this is the symbol which is used for representing the compressor, like this. Draw a line, vertical line, like this. So this is a compressor. So the area is gradually decreasing, like this. And keep in mind, always the inlet you should show at the larger area here, like 1. We cannot show the inlet at this point. If you show inlet here and if you show outlet here, it will become expansion. The area is gradually increasing. It should not happen in the compressor. As the name of the device, that is compressor, means it compresses the fluid. So during compression, volume decreases. So that is compressor. So next, second component is combustion chamber. In the combustion chamber, we will be supplying fuel. The working explain, I will explain, don't worry. So second component is combustion chamber. There is no symbol specifically it is used for combustion chamber. You draw one small square box or rectangular box, then you write CC, that is combustion chamber. Then turbine. So there is a standard symbol in the mechanical industry which is used for representing the turbine. So turbine will be represented like this. I will draw here. First you draw one small vertical line. Yes, this is a turbine. Okay, in the turbine and compressor, what is the difference is, here in the compressor the area is gradually decreasing. In the turbine, inlet will show here and area is gradually increases, and outlet will show at this point. And one more point, one more difference between compressor and turbine, the symbol is, the turbine will show the shaft, right, the generator. Here we have shown the shaft. So that is turbine. And in the compressor, we will show the shaft on the left hand side. Understood how to represent the compressor and the turbine, because many students get confused in the exam. So they will write in place of compressor, they will write turbine, and vice versa. Okay, so let me explain once again. So compressor is area should decrease and inlet should be at this point on the larger area, and outlet will be at the smaller area, and shaft will be at the left hand side. And for turbine, inlet will be at the smaller area, outlet will be at the larger area, and the shaft is should be at right hand side. Here there is a larger area. In both the case, compressor or turbine, the shaft connection is at larger area. That is a hint I will give. Here is also a larger area. Here is also a larger area. Okay. Here is a small white color. I can see this is shaft. Okay. Now we'll understand the working principle of gas power plant. Okay. Let me erase all these things. Okay. First point, what you need to understand here is, in the beginning of the cycle, beginning of the operation, beginning of the working of gas power plant. So first, initially, we need to supply a electrical energy to a motor. Some device we have to supply electrical energy. So this electrical energy motor converts to mechanical energy to the shaft. That shaft is connected to compressor. It is beginning of the compressor, means for start of the engine, start of the cycle. Because before starting the engine, there is no combustion. When there is no combustion, no question of gases in the turbine. When there are no turbine, no gases in the turbine, it will not generate any mechanical work. So for that reason, initially we'll supply mechanical work on the compressor. So work is done on the compressor, WC. So once the compressor is start functioning, the compressor sucks atmospheric air at pressure P1. So P1 is a pressure of the fresh air, atmospheric air, or at the inlet of the compressor. So as compressor device increases the pressure of 0.1 P1 pressure to P2. So at the outlet of the compressor, the pressure is P2. So P2 is greater than P1. Keep in mind. So what is compressor? Once you supply some mechanical energy, mechanical work, the compressor starts. The compressor sucks atmospheric air. It will draw the atmospheric air, that is fresh air. The pressure of the atmospheric air is P1 and it compresses to high pressure, that is P2. So P2 is greater than P1. And dear students, same you observe the PV diagram. So point number 1 is here. So this is pressure versus volume diagram. As I said, pressure will be increases. So point number 1 is here. Point number 2 is here. Pressure increases. This is P1 and this is P2. Pressure increases. Now you can ask a question, what is the type of this process? What is the name of this compression process? So process 1 to 2, I will call it as a reversible adiabatic compression. Reversible adiabatic compression. So what is another name of reversible adiabatic compression? What is another name of reversible adiabatic compression? Anybody please unmute yourself and tell me.
Isentropic.
Isentropic. Isentropic. Very good. So both are same. So reversible adiabatic compression is same as isentropic. Isentropic means entropy remains constant. So 1 to 2 in the TS diagram, entropy is constant. Just look at this diagram. Here it is S1 is equal to S2. Entropy is constant. So I have to show the arrow mark upward. And here it is also upward arrow mark. So that is first process. Okay, what is first process? In the first process, it takes place in the compressor. So once you supply some mechanical energy, so compressor takes the atmospheric air at pressure P1 and increase the pressure to P2. Okay, next, second process. And keep in mind, my dear students, these values P2 is greater than P1. And we know that PV is equal to mRT. This is the ideal gas equation. As the pressure increases, so there is slight increase in temperature also, according to ideal gas equation. So that is the reason here T1 is less, T2 is more. So there is a slight increase in temperature during 1 to 2 process. That is upward arrow. Next process, second process is combustion process. Combustion you can call, you can heat addition, or you can use the word 2 to 3 is combustion process. So to get the combustion, we are supplying fuel. We have to supply fuel. So this fuel may be any fuel, it may be solid fuel, gaseous fuel, whatever it may be. It has some calorific value. Keep in mind, calorific value. So once you supply the fuel to this combustion chamber, and we are supplying high pressure air, that is P2 is high pressure air. P2 is much greater than P1. So high pressure air mixed with this fuel, then combustion starts. Means heat releases. Heat is added to the air. So here we'll get gases. Initially at point number 2, it is air. Now we are supplying fuel. When fuel and air mix together, you will get gases. That is, these gases are going to the turbine. That is again gas turbine power plant. Why you call it gases? Gases are going to the turbine. Okay, if you are assuming it is ideal case, air standard, you are assuming it is also air standard cycle, then there is no gases formula. Assume it is air. Air will be mixed with heat exchanger, and heat will be added in the heat exchanger, then air enters to the turbine. When you are assuming it as air standard cycles, but in actual case, in the practical case, it is gases will be formed. These gases enters the turbine. So now 2 to 3 is heat addition process. I will write here heat addition process, or you can use combustion. Now the question arises, what type of combustion it is? Here 2 to 3 is constant pressure combustion process. Keep in mind, constant pressure combustion process. So we have discussed one air standard cycle where the combustion is at constant pressure. What is the name of the cycle where the combustion is at constant pressure? One cycle we discuss air standard cycles, Otto cycle, diesel cycle, and dual cycle. In which cycle the heat addition is
Diesel cycle.
in which cycle?
Diesel.
In diesel cycle. But in the dual, part of heat addition is at constant pressure, the remaining part of it is constant volume. Okay, so that is second process. Third process is expansion, that is 3 to 4. Okay. So 3 to 4 is an expansion process. 3 to 4 is reversible adiabatic. In the turbine, compression takes place or expansion? The turbine, exactly opposite of compressor is turbine. In the compressor, compression takes place. But in the turbine, expansion takes place. Keep in mind, expansion takes place. So what type of expansion? It is reversible adiabatic. It is also called as isentropic expansion process. So here 3 to 4 is isentropic expansion represented with curved line in the PV diagram. So as you said, it is isentropic means entropy constant. So during 3 to 4, the entropy is constant here. Next. So these are 3 processes. Now there is no 4th process we have represented in this block diagram, but we have shown in the PV diagram and as well as in the TS diagram. What is that 4 to 1 is? It is constant pressure heat rejection. If you consider one more device, if you take one device between 4 to 1 and you make it is a closed cycle, then it will be heat exchanger. So in this heat exchanger, it is at constant pressure heat rejection. So constant pressure heat rejection is 4 to 1. But in the real industry, there will not be any devices because these gases are going to atmosphere. These gases are going to atmosphere. So in the atmosphere means constant pressure. Okay, if it is at 1 bar, it may be 2 bar. Okay, depends upon the type of the engine, type of the cycle what they're doing. Okay. So there are four processes. So let me add the last one. Fourth one, heat rejection process. Heat rejection process is constant pressure. So in simple word, we can say that there are two isentropic processes, two constant pressure processes. Okay. So we'll discuss once again what is Brayton cycle. Brayton cycle is also called as Joule cycle. Keep in mind, it is a Joule cycle. So it consists of three major components. First one is compressor, second one is combustion chamber, third one is turbine. So compressor and turbine both are mounted on the same shaft. As you can see here, the shaft, the white color, this is the shaft. Okay, now you can ask a question, why compressor and turbine both are mounted on the same shaft? Because we need mechanical energy to run the compressor. And I am getting some mechanical work, mechanical energy from the sorry, from the turbine. For example, here I am getting 50 joule of energy from the turbine. So part of 50 joule of energy I will transfer to the compressor through this shaft. How much? 120 joule of energy I will transfer to the compressor. The remaining 30 joule of energy I will get in the generator for generating power, generating electricity. Otherwise, what we need to do is separately we have to run the compressor and separately we have to run the turbine. So instead of wasting energy, instead of supplying external or extra heat, extra work, extra mechanical energy, so what we do is we are supplying from